Welcome, everyone. Today, we continue our SDV practical webinars with the next episode focusing on SODA.Create, our powerful tool for mastering requirements, traceability, and architecture in software-defined vehicles. In this session, we'll take a deep dive into how SODA.Create helps you manage design specifications, link requirements across multiple levels, and maintain architectural clarity throughout your development process. I'm excited to introduce my colleague, Alexey Yakovlev, product lead SODA.Create, who will walk us through the platform with a live demo and answer your questions in Q&A session. Let's get started.
Hello, everyone. Thank you, Ksenia, for the introduction. So again, my name is Alexey. I'm product lead of SODA.Create. And that's the fourth webinar in our series, and the second specifically about SODA.Create product within our SODA-V solution. And just to reiterate, the first webinar about SODA.Create was basically overview of what is SODA.Create, what are its main goals and focus. And I also just shown basically an overview of what is currently available in tool. And today I will provide more details specifically about how the data is structured in SODA.Create. So what are the different objects used in design, such as requirements and design object specifications, how they're connected, and what are the kind of current capabilities of the tool which you can use around those design objects, and how it can help to create a quality, a design specification of the good quality with no issues in data traceability and data integrity, and still this process would be quite fast and easy, even not for the most experienced people to go through. So let me now share my screen. I hope you can see it now. So that's how our studio looks like, SODA-V Studio, and part of the studio functionality is related to SODA.Create, as I explained on the previous webinars. And just for maybe people who didn't watch the previous episode, SODA.Create is basically systems engineering tool with a focus on requirements engineering and model-based design for the vehicle applications, features, systems, and software. Well, in this case, what are the main objects used in the tool? So two main types of the objects are requirements and design specifications. And requirements could be of different levels and of different types. Currently, because we're focusing on kind of automotive market, and in general on our tool is to help design the product, some sort of vehicle product, whether it's actually a car or I don't know, a van or some aerospace vehicle. It doesn't really matter. But in any case, considering this, we have currently 3 levels of requirements in our tool, and we'll be adding a fourth level later on. So those 3 levels are basically vehicle requirements, feature requirements, and system requirements. Vehicle requirements are quite easy to understand. those are kind of end-to-end requirements for your vehicle as a whole. So it's a product level requirements of different types. It can be some high level attributes or use cases for the vehicle. So for example, what is actually the type of the vehicle, what are the target markets, what are kind of the high level end-to-end use cases which you can derive product features from later on, and so on. It could be also, as you see now on the screen, some derived requirements from the applicable regulatory documents. So for example, here we have requirements derived from UN regulation number 13H. That's so basically this level describes product level stakeholder requirements, product level constraints such as regulations or maybe some hardware systems that are predefined and should be used during design. On this level, we can also define such requirements as a functional safety goals derived from the functional safety analysis or cybersecurity goals. So those are basically high-level requirements which then used as a design inputs for the kind of solution design process, for the systems engineering process. And what I'm showing to you right now, I explained it on the previous webinar, but basically it's a requirements part of the vehicle feature specification document. And that's right now a good moment to describe the second kind of major type of the objects which we have here. Those are so-called design objects. And they are of the three types. It's either vehicle model itself, or it's the certain version of the high-level vehicle function, or as they are called here, vehicle features, so basically product features. And it also can be a version of the vehicle system as well, as a kind of lower level design object. And we're also working on allowing to make even more detailed design, so to introduce like a component level design objects and requirements with the focus, of course, on software components. But basically, this what is the difference between those two types of the objects? So basically, a requirement is considered a simple object. So for example, this is my requirement. Let me just introduce some random change here. And this has created the second revision of the requirement. So basically, the requirements are considered some sort of atomic design objects. When I introduce the change, it automatically applies it, creating the new revision. Basically, the new independent design objects, so now I have two of them, revision 1A and revision 2A of the same requirement, and I can choose which one to link and use in any design document which I have in my environment. So those are the simple objects. Each change creates a new revision, which is immutable, so I can't modify it. If I apply modification, it actually creates another revision. And the non-requirements design objects like, again, vehicle itself, vehicle features, vehicle systems, they are more complicated in terms of source control, let's say. They are under branched mechanism. So for example, here I have my exterior lights, brake lights example of the specification. And you can see that there are different versions of the specification. Those are basically different branches. So for example, I can create a new one. Let's call it main. And this created the new version of the new branch of the same feature, or I can actually fork this object to basically clone it and have another feature with another like ID, etc. But essentially, in those versions, not revisions, right? I can introduce changes which do not create a new revisions. For example, here I can select. Here I can select, let's say, or create another like revision of the requirement. And now basically I changed the content of my specification. Now I have revision 2A instead of 1A here. But this change was introduced in the same branch, and I just can see this change in my history of changes, right? So it means that when I create a new version of the design object, it's not immutable. It's basically an open branch. It's a draft document, and I can apply changes continuously in this document. There will be a history of changes, and when needed, I can just lock it, basically make a baseline. So how do we work with these two types of the objects? Well, so first of all, design specifications and design objects are quite different. So, for example, currently in the vehicle feature specifications, which is S1, product level function, basically, product level design objects, we have two sections, which are requirements and architecture. Let's say in the vehicle systems, there is only requirements section for now, and we will introduce architecture section after component level, which we are working on now, will be here. But in essence, the mechanism is the following. So inside your document, there is a certain content, right? And for example, the content of requirements section is basically two types of objects: links to the requirements. So for example, to demonstrate it, let me just remove this requirement from this feature. And then I can either create a new one here, obviously, but I also can search for it and add it back. So those are not just kind of text written here. Those are links to the requirements objects, and then I can basically search my library of requirements and add different requirements to my, let's say, feature specification, depending on my needs, right? So that's the first thing we can do here. We can, for example, in this section, link requirements of two levels. And the idea here is that, first of all, from like high level vehicle requirements, you understand what are the vehicle features needed. You, let's say, create the feature specification, and then you add those design inputs on the vehicle level here. And the idea is they should be taken into account during the downstream design. And how we check that they're taken into account? Well, it's possible here to create derived links. So basically create a traceability matrix. And as you see, for example, this requirement doesn't have any downstream, let's say, connections here. And it's highlighted as a compromise because basically I said I want to meet this requirement by this function specification, but failed to define what is the decomposition, right? What is the downstream design behind it? But I can just quickly do it if needed, and thus create these traceability connections. And as you see, now I can basically easily check what are the associated requirements from which this has been derived from. They are kind of shown here, highlighted, sorted at the top, and vice versa. I can quickly check which are the low-level requirements this regulation has derived. So what I wanted to say is that in this section of the specification, you can link requirements of different types on two levels, and then create derived link objects to show the traceability and decomposition, and have these highlights if there are basically data integrity issues, if your requirements has not been taken into account. And in a similar way, if we for now ignore that there is an architecture here, we can just do the following. So we can, for example, see again the requirements of different types on two levels. In this case, those are the next two levels. So basically vehicle level requirements, but specific to this feature. So basically detailed feature requirements, and system level requirements in this case related to exterior lighting system, which are needed to be kind of implemented by exterior lighting application or system or E2, it doesn't matter in this case, in order to support this design. And again, you can see the traceability, you can quickly update the traceability. So the mechanism is similar here. So those are kind of how requirements work, and what is the point of traceability, how you can create it and use to visualize your kind of design, let's say, dependencies, right? Now about the architecture. So basically, okay, I have my design object, high-level vehicle function, which is in this case brake lights main branch or main version. There is a certain level of product requirements associated with it. Basically, those requirements I will need then to validate the whole vehicle, kind of the integration of systems against, right? But for example, in the case of automaker, the usual scenario is that you kind of, as a vehicle owner, define the product scope, you decompose it, or probably it's like a solution architecture team or systems engineering team. You decompose it into the kind of different functions, define what are the functions and what are the versions and scope to be delivered, for example, for the certain milestone of the vehicle program. And then you need to actually understand how those requirements, function by function, will be implemented by the vehicle systems and components. And mainly it's needed, well, first of all, to check if design is kind of can be met by the available systems and components, but also to just basically derive the system deliverables from this process. So basically you understand what are the vehicle features needed, you then create requirements for each of them, you then understand what are the vehicle systems needed and what are the requirements specifically for each of the system in the context of the given feature. And then you can basically merge system requirements and see that there are no conflicts from multiple features for, let's say, exterior lighting system or HMI system or some other system, and then ship this deliverable for the implementation by either like in-house software team or some supplier. It doesn't matter. So it's a very important step in the process here, because here we basically understand what are the systems needed and what they should do in the context of the specific function. And this is kind of, this will have major impact if done correctly or incorrectly on the actually software product you will receive after the implementation, and how much kind of time and effort you will spend trying to validate and fix it. So to kind of make sure that the system requirements and in general, like integrity and feasibility of the design have a good quality after this design process and don't require a lot of fixes later on during the development and validation phases, we decided that it's beneficial to have this kind of architectural tool built in right here together with the kind of requirements management, and have this explicit traceability and connections and kind of integrity issues highlights between the requirements and architecture in one place. So it's a more like holistic view on the design specification you get. And how it works, well, in this section, we again have different types of objects. Well, first of all, you kind of link to the diagram the instances of the vehicle systems. So, for example, in my in this kind of demo environment with demo data, I have some systems in my catalog. So, for example, like I have, let's say, I don't know, stoplight, and then already here I've added multiple instances of stoplight in my brake lights specification, so like rear left, rear right, central. Let me just show how can I quickly add another one. So for example, for some reason I have, I don't know, center low mounted lamp. It's probably not the case, but let's just add it to see how it works. Now you see that I have an additional instance of the same system and on my diagram, and as you can see, it already has like 2 ports added automatically. That's because the underlying mechanism and how to use it is the following. So when you add the kind of first instance of some system to your design specifications, to your architecture diagram, it actually creates the dedicated feature branch of the system. So it's basically a dedicated version of the system, which then use as a prototype for all instances in this specific diagram. What this allows to do, first of all, it allows to synchronize all of those instances. Of course, if I, for example, add some configuration parameter, just let's add some random parameter here. So let's say I will have like wind parameter with default value 10. This parameter value override can be different for different instances. So for example, here we'll have like 12, and in some other instance, I will have another value. But in general, the instances of the system are synchronized because they reference exactly the same prototype. So you see, I have my parameter added in all of them, and I can just set up the different kind of settings. But basically, so first of all, creation of this dedicated feature branch, which then used as a prototype for all instances, allows for kind of synchronization of the instances. But also it allows to basically I can define here the like requirements, ports, parameters, overrides in a way that I add here in this specific version of the system only what I really need the system to implement in order to support my brake lights. So for example, I can have multiple vehicle features like brake lights, headlights, like reverse lights, indicators. All of them use exterior lighting, like distributed application or ECU, depends on the vehicle architecture. But ideally, I define the requirements in each feature branch of exterior lighting, which has little kind of intersections. So those are requirements only needed for the specific vehicle feature. And then I merge all of those features together to combine this kind of overall deliverable specification for exterior lighting, which should support all my features. I will have very little or none conflicts between those requirements because they are managed in independent branches, and by design, they should have a lot of intersections and conflicts. But basically, as I was saying, the main type of objects in the architecture is an instance of the vehicle system, which reference the same prototype, so-called feature branch in this case. In case it's instance in the vehicle architecture, it will reference not a kind of branch or specific kind of defined version of the system from the catalog. What are the other objects here? So first of all, those are obviously connections. So after I, let's say, added ports, it can be either receiver or sender ports to my system, it kind of automatically was synchronized to all instances, and instances of the ports are also created. And using the instance of the ports, I can now define the integration requirement. So this connection I have populated here, it's called a direct connection. And it's basically a requirement. It means that on the vehicle, those two systems should communicate should have a certain data exchange. Otherwise, this feature will not work. So the second type of the object you can create and use on the diagram in the feature architecture or in like vehicle architecture is the connection between instances of the ports. I already mentioned a value override of the parameter. It's also kind of architectural object. It belongs to the instance of the system. What else? And the last type of the object which I can use here, let me just add it because it hasn't been added in the specific demo case. It's a so-called feature port. So I can define ports not only on the system level, but also on the feature level. Why it's needed, it basically allows to more kind of easily manage my design process, to define the boundaries of the vehicle functions and basically not duplicate the requirements and scope. And I can use those feature ports to basically create another type of connection, which is called delegation connection. It basically means that I have my high-level function. It has some abstract definition of the ports to separate the scope and define dependencies between different functions. And then I can say, okay, I don't have, let's say, for this receiver port on my system level, the connection, the data flow, which supports it directly in my design because it's out of scope. But I can remove basically the highlighted integrity issue. So as you see, this port is highlighted as not connected. It's a mistake. But here it's by design. I don't want to define what is kind of produces the data which feeds to this receiver port. But I just say that it's an external data to this function. So I can just define my interface and don't design end-to-end what is this data, how it's produced, who produces it, etc. But obviously, when I put my features together then in the vehicle, I should resolve those dependencies connecting those feature pods. Yeah, so that's basically how the architecture works. And just to mention some additional benefits we have here. So let's say, well, I already shown that the kind of requirements which don't have downstream traceability, they're highlighted as having issues. The ports which don't have connection, they're also highlighted. And here you can see, for example, that in this kind of demo data, I just added like parameter and 2 ports into the feature branch of my stoplight system. And haven't actually defined any requirements. So those are basically unused API I have. And it's also highlighted. It's a warning in case of parameter and receiver port because I have, okay, I don't use it, but it's not maybe critical. But for the sender port, it's critical. So it's highlighted as an error. I basically defined the outgoing data, but didn't say anything about how it's actually produced. So in order to remove this warning and in general to demonstrate you what we can do here, let me just create a certain requirement. For example, we need to do something with the stoplight command interface, take into account this parameter, and define the behavior of lamp feedback outgo interface. So how it looks like, so for example, I can say that if my stop lamp command is, let's say, activate, and my parameter is, let's say, true. For example, it's, I don't know, just parameter which allows to disable lights control in general. Then my lamp feedback, well, obviously there should be something here also about the current because it's actually lamp feedback, but That's just an example. And then my lab feedback should be active. Well, it's a bit fictional requirement, but what I want to demonstrate here is that in the requirements, you can directly reference those kind of more formal, like software level objects related to the architecture, such as port and parameters. So basically, in your requirement specification, you can use the available interfaces, whether it's like basically broadcast interfaces like receiver and sender ports, or it's calibration interfaces like the parameters. And this also allows for the more easy way to create a quality design. Because, for example, let's say, well, it's actually unit 8 parameter. So, well, let's say I somehow modify my parameter, right? So now it's actually a vector with like 2 rows. So basically, this does not anymore. This is not compatible anymore with my requirement, because in my requirement I used the previous revision of this parameter, and after my changed my revision, basically there is a highlight that there is a potential issue. So when I use this parameter in the requirement, it was different than it is now, and I can either update my requirement, or I can say, actually, I want the previous revision because this new revision breaks my requirements, similar to the pods. So basically, there are different ways how having this kind of data populated and connected in a more formal way, in a more explicit way. You can provide to the designer, to the architect, the immediate feedback about potential mistakes that might be made during this design. Actually, this thing about parameter I just shown, I used the test environment right now. It's not released to the production yet. The release to the production will be this week. So yeah, feel free to check it out. Now it will allow you to actually create the, let's say, library of data types, including custom data types like enumerations. It will allow to use these data types in your calibration parameter specifications. So it's quite a good feature. Very close, allows to create a very close specifications to actually how it will be implemented in software. So for example, as you see, I can choose my kind of default data type or create a new enumeration. So it's quite powerful. Check it out this week, I guess. It will be on production. And as I mentioned before, why it's important to have this kind of feature-driven approach to the design when you work with separate feature branches of the system and create the kind of basically feature requests for those systems. Well, it allows to be more flexible in your vehicle design, so you can just define on high level what are the vehicle functions needed, which of them will be available kind of in which milestone of the vehicle program, manage the versions to flexibly introduce like updates and hotfixes, major changes, minor changes, etc. And then it allows to conveniently basically scope the actual content of your system using those requests from different features. And it also allows to kind of for actually like let's say people who manage this requirements project, or for the people who then receive it as an input to show actually the traceability. So I used my system in kind of 3 versions of this feature I have in this environment. Had some traceability connections, and you can see those here as well. So those traceability connections from feature level to system level has been created in some feature specifications, but I can also review them here. And I can also review easily what are the feature versions supported by my version of the system. As you see, there is none here. but I can quickly understand what is wrong, basically. So, for example, I want to support the let's say main version of my vehicle feature specification by the system, and I can quickly see what is missing. So basically, there are kind of 3 parameters missing in the current scope of my system, and actually 4 requirements have a conflict. They have a different revisions. And similarly, if I want to support multiple, let's say, features or multiple versions of the same feature, I can do it basically in bulk to just understand what is the overall scope of feature requests and what are the conflicts. So, for example, there is some conflict between the feature request itself, between different revisions of the same requirement, and there are conflicts or missing requirements in my system. So what I can do, well, first of all, I can quickly add everything without the conflicts, and then I can decide what are the requirements I actually want in my system after all. So, for example, I actually understand that, okay, I need to fully support this main version of the brake lights, and now it's fully supported. And this feature is outdated. I don't need to worry about it. I just remove it here. And now, as you see, we can check that our exterior lighting main version fully supports 2 versions of this feature. And if I go back here, I can see that, okay, so in my architecture, I have exterior lighting, instance of exterior lighting system, and actually the main version of the system fully supports this feature branch, this design. So that's quite a convenient way to have these different kinds of traceability between the data in the tool, which is enabled again by our approach. So we have requirements as independent objects. We can create traceability links. We have architecture with instances, which we were able to link requirements directly in those, basically prototypes for those instances. And then it's quite easy to understand what actually should be implemented, what are the issues, and fix them. Well, I guess that's all what I wanted to explain about SODA.Create today. As I mentioned, this release with software parameters and actually a few more updates. So, for example, you will be able to select which type of AI model should be used for different features. On the previous webinar, I shown it that you can generate a test for the requirement as an example of one of our AI related functionalities. And now in this release we will have this week, you will be also able to select what is the actually model which should be used. So, for example, like Cloud or whatever we will add to our production release. Yeah, so that's probably everything I wanted to talk about today. Let's maybe jump to the Q&A session now.
Very nice. Thank you so much, Alexey. Very insightful. And we have our first question. Would I be able to import an existing requirements components in a bulk way using CSV, JSONs, any other formats? For example, I'm using requirement URG with Jira. It's possible to export them to CSV.
Yeah. That's a great comment. So we're now working and very close to actually allowing to do this right from the user interface. So you will be able soon to just export the list of requirements from our tool to CSV format and import requirements from our tool to CSV format. It's not in production yet. It's not released to production yet. For now, it's with our customers if they kind of don't want to wait for this functionality or they want to start using our tool kind of right now and don't want to kind of recreate all the requirements manually. We just help to do it basically with our API, without user interface. But again, soon in spring for sure, we will have a release which allows import and export in CSV. And we also have some feature requests to support also rec-if format, basically docx format. So we'll be also working on those in the nearest future as well.
Great. And I have a question from my side. From your perspective, what kind of engineering tools SODA.Create might replace?
I mean, I think it's a good alternative for the number of products, like, for example, JAMA or DORS or some parts of the vector prevision. For sure, it's much better than Yogi requirements in config. So there's some, spreadsheets in Excel. Basically, it's also, I think, a good alternative for the combination of, for example, Simulink requirements plus System Composer. Because the idea when we created and, well, introducing the new functionalities to SODA.Create is that it's basically a streamlined tool which allows to create a good quality, detailed design for the vehicle, like functions, electronic systems, and software, modern, convenient, and kind of flexible for the engineers to use, and also like accessible without too much unnecessary complexity introduced. So it's easy to just start using it. The onboarding is quite simple, it's intuitive, and it allows basically to get a job done with very, let's say, democratic pricing model, and without a lot of requirements, to set it all up, to understand how it works, and to get your team on board to do it.
Got it. Thank you so much. I think today it was a really deep dive into the tool. Yeah, I hope everyone enjoyed this. I enjoyed it myself. Thank you so much. And
Thank you,
yeah,
Ksenia.
we'll keep going. Yeah, and please come to the next series.
Yeah. Stay tuned. Short, there will be update about our next release with parameters and some other features, as I mentioned, released to the production. Thank you.
Great. Have a nice evening, everyone. Thank you, Alexey.
Bye-bye.
Bye-bye.